Hello, my name is Chris Gerlinsky. I'm talking today about how I cracked digital, cable, and satellite TV security. I studied an access control platform that's widely used across Canada and USA, one of the two common platforms used in cable TV, as well as being used in satellite TV, one of the two Canadian satellite TV operators. As far as I know, the system has been secure since its introduction in the late 1990s. So I was curious if I could understand the system based on the older set-top boxes. Some of them are 15 years old and they're still in use. And those devices haven't been upgraded with any security hardware in that time. So I started to look at how the system works. So satellite and cable digital television are pretty similar for the most part. There are a variety of signal modulations used. The relevant ones here are QPSK at about 27 megabits, and 8PSK TurboFEC at about 38 megabits for satellite, and QAM256 at about 38 megabits for cable. There's also an out-of-band channel used by cable, which is QPSK at 2 megabits. The out-of-band channel carries subscription management, program guide information, firmware upgrades, etc. While you change channels and the cable box tunes to different frequencies, the out-of-band channel remains tuned, so the box continuously receives this data no matter what TV channel you tune to. In the satellite TV, this type of data is included within the main transport stream. The video is sent as MPEG-2 or H.264 transport stream. This is a standard format for carrying video streams, so it can be played by any hardware video decoder or a software decoder. The encryption system is DigiCipher 2, and this system doesn't follow the DVB standards that are normally used in the rest of the world. The MPEG transport stream is made up of packets of 188 bytes. Each packet is a PID. This is used to differentiate different types of data. The PIDs range from 0 to hex 1F, FF. Each of these PIDs carries either an MPEG packetized elementary stream, that's a video or audio stream, or the PID may carry one or more service information tables. Service information tables have an 8-bit table ID and a CRC on them. The table ID identifies the type of data that's going to be expected in the table. Some of the common tables that are found is table 0 is a program association table. This is a list of all the programs on this transport stream, and this list has a PMT PID for each program. The table 2 is the program map table, and this contains a list of the packetized elementary streams that make up the video and audio for each channel. The ECM PID is where the entitlement control messages are sent, and they contain information that is used to generate the key to decrypt the packetized elementary stream. This system uses two types of ECM. Table hex 40, I call ECM 40, and table hex 41, I call ECM 41. On PID 1, there may be one or more conditional access tables, and these tables identify a PID that carries EMMs, entitlement management messages. These messages are used to set the access rights for individual set-top boxes with subscription information, such as what channels are available. This is a hardware interface to receive satellite data. This is a GenPix Skywalker 1. The DC2 QPSK modulation isn't really widely supported in the USB devices, and the 8PSK TurboFEC is even less common, but this GenPix device has a Broadcom demodulator that supports both of these modes, and it works really well. The Linux drivers for it do have to be recompiled. There's some patches for it that have been published by Update.ly. There's some links there, you can find that online. For cable, there's a variety of different adapters that support the QAM256 demodulation. I use this USB HVR 950Q tuner. But tuning the out-of-band channel is generally not supported by these interfaces. In a cable box, it's handled within their integrated chipset, and for the clear QAM these devices are marketed for, the access to the out-of-band isn't required, so they don't put that tuner inside. With the satellite and cable interfaces, DVB Snoop can be used to view a lot of information about the transport stream. It's really enough information to be overwhelming. So the trick to using it is to be able to sift through the output for relevant information. And DVB Snoop also does not recognize all of the DC2 tables because DC2 is such a non-standard system and DVB Snoop is targeted for the standard systems. So it might not tell you everything about this transport stream, but it is a useful tool for all the information that it will provide to you. So DVB Snoop and most other tools and documentation are designed for the DVB standard or other standards like ATSC. And DigiCypher cable and satellite systems use a lot of non-standard tables. So for cable TV, some of them are standardized by SCTE 65. There is no BAT or SDT, as there would be in DVB. Instead, there's a virtual channel table that maps transport streams and programs to channel numbers. And the electronic program guide is also not DVB standard. So you don't even get current and next program information in any kind of a standard format. Another cable TV adapter is the HD Home Run Prime. It's a network-connected 3-tuner device, and this one has cable card support. The set-top boxes I studied predate cable cards, but newer boxes do use cable cards that support the DC2. With cable card support, that means that the HD Home Run Prime has the tuner and QPSK demodulator to handle the out-of-band channel, so it can pass that data to the cable card. But the HD Home Run doesn't make that out-of-band data available other than via that cable card interface. To access the demodulated out-of-band data, I tapped into the HD Home Run Prime with the cable card inserted and connected a logic analyzer to data and clock signals. I wrote software using the Salia SDK to capture the QPSK demodulated data, perform the deinterleaving, derandomization, and forward error correction, and output an MPEG transport stream. This is all defined in the SCTE 55 standard. So using an HD Home Run Prime connected to Salia, connected to a PC, running this software, the output is a standard 2 megabit transport stream. And this transport stream includes the conditional access management messages and the program guide information and all this kind of service information. So in the MPEG transport stream descrambling, there's 2 bits in each packet that indicate if the packet is scrambled with an even key or an odd key, or if it's not scrambled at all. This key is changed at very short intervals. DVB systems would typically change it every 5 to 30 seconds. On the DigiCypher system, they change it every 133 milliseconds, or sometimes they slow it down to 1 second. The key used for decryption alternates between even and odd. The odd key is in use while the even key is updated. Then while the even key is in use, the odd key is updated. An encrypted transport stream is sent via the cable or satellite. It passes through the descrambler inside the ACP, the access control processor, and the result is a decrypted transport stream that can be played by the MPEG decoder. This descrambler uses a working key. This is a 56-bit DES key. It changes every 133 milliseconds. And the working key is generated by encrypting the frame count value that's found in an ECM40 packet with the program key. The program key, another DES key, comes from the ECM41 message and is encrypted with the category key. The program key is unique to each channel and changes daily or for each pay-per-view event on a pay-per-view channel. The category keys, which are also DES, are shared by all the set-top boxes that are authorized for any channels on this provider. The category key is sent to each set-top box individually in an EMM. The category key typically changes monthly, but actually many of the cable operators aren't changing their keys very frequently. To decrypt the EMM, in order to get the category key, seed keys are used. Each set-top box has a set of 56-bit DES seed keys in battery-backed RAM that are initialized during manufacturing. For the lifetime of the set-top box, these keys are used to secure EMMs. So this forms a chain from the seed keys initialized during manufacturing and never changing, all the way to the decryption of the MPEG transport stream. Inside a set-top box for a satellite system, we can see the main components. The signal enters the tuner and is passed through the demodulator, which outputs a serial transport stream. The transport stream passes through the ACP, the access control processor, and is then sent to the MPEG decoder, which outputs the video signal to the TV. There's a 68K microcontroller that acts as the set-top box main controller, it communicates with the MPEG decoder as well as with the ACP via an SPI bus. A battery is used to provide a backup power to the ACP, so it always retains its RAM contents even if the box is unplugged. There's a TV pass slot near the power supply. This is an upgrade slot with a card edge connector to allow for security upgrades. The system has stayed secure, so the TV pass slot was never used, and the newer versions of the set-top box, they actually took this out. Inside a cable set-top box, it's similar to the satellite set-top box, but cable boxes tend to be a little bit more integrated. The signal enters the tuner and passes through a Broadcom chip that handles the demodulation, and this will also handle the MPEG decoding after the transport stream is sent through the ACP for decryption. A 68K microcontroller acts as the main controller again. It talks to the ACP via SPI. There's the battery for the backup power to the ACP and also for some non-volatile RAM used within the cable box. And there's a TV pass slot that's underneath the board in this box, but again, in the newer versions of the boxes, they no longer support the TV pass slot. The cable set-top boxes include a second tuner, which is used to receive the out-of-band data. The out-of-band tuner operates independently of the main tuner and on a separate frequency range. So this way, it always stays tuned when you're on any channel, and this is where all your firmware upgrades and your EMMs and all this kind of stuff comes through. This is the ACP chip. It's a 100-pin TQFP package. From the markings, we can see it's a custom system on chip made for General Instrument Corporation, GIC. All the decryption is performed by the ACP, and all decryption keys are kept only inside this chip. The newer set-top boxes have newer versions of this ACP. My study focused on the original chip that we see here. As long as these set-top boxes are actively used, it's still a relevant target. Whether the newer chips include more advanced security features, or if they exist only for cost saving due to die shrinkage, I don't really know. Some of the interesting pins on the ACP are labeled here. Pin 1 is marked at the top left corner. There's an SPI slave interface on pins 1 to 5 that's used to communicate with the main controller. There's a battery backup pin that's connected to a 3-volt battery that keeps the RAM contents intact. And there's a serial transport stream input on the pins 88 to 92, which receives the data from the demodulator. And then there's a serial transport stream output on pins 28 to 33, which sends the decrypted transport stream to the MPEG decoder to be output to the TV. To monitor the data passed between the set-top box main controller and the ACP on the SPI bus, I use an Atmel XMega development board. I configured 2 SPI ports as slave, with the master out slave in signal connected to one, and master in slave out signal connected to the master out slave in input of the second port. So from one port, I get bytes that are sent from the set-top box controller. From the other port, I get the bytes sent from the ACP. If I want to talk directly to one of them, I only have to connect both the pins properly for the SPI, and I can hold the main controller and reset, and then you can talk to the ACP directly without it interfering. At one point, I wrote software for an AVR32 device that has a synchronous serial peripheral that could handle the 27 megabit serial transport stream. My implementation was a little bit ugly, but rather than clean it up, I was able to use it as it was. It was limited to a 64 kilobyte chunk of replay and logging, which was good enough for what I needed to do. What it did show me is that the full transport stream passes through the ACP. There's selected pins that are decrypted. And so on the output of the ACP, we have the entire transport stream, but one of the programs has been decrypted. So my AVR32 logging interface had limited use, and later on I did some more thorough research, and at that point I pulled the ACP off and put it on a breakout board, and then I could control the serial clock, and it was much easier to use just an XMega. By logging the SPI bus between the main controller and the ACP, we can see that information about the current access level is sent from the ACP. The ACP also receives their EMMs from the SPI bus. The EMMs are filtered by the unit address, the set-top box serial number. So the ACP only receives messages intended for that specific box. There's a command 4, which tells you what the current category key epoch and the key select is. There's a command 5 that includes the unit address. Command 13 gives you some information about what subscription tiers are authorized. There's also the set-top box main controller. Tells the ACP which PIDs it should decrypt, and it tells it which PID has the ECMs, and that's done by the SPI interface. The ACP never sends any keys on the SPI bus, and it only receives the category keys in encrypted EMMs on this bus. So next I started an invasive study of the chip, studying it under a microscope. Now, microscope costs can range from hundreds of dollars to tens of thousands of dollars, or even higher for electron microscopes and this kind of thing. I used a Mitutoyo FS70 microscope for the photos you'll see here. The FS70 is used typically for microprobing, but you can use it for other things also. I used it because I had it available to me. Really, for studying this level of technology, you could use a lot more basic equipment, but if you have something higher end, it's always nicer to use the higher end stuff. To look at the chip under the microscope, I have to decapsulate it. So I use fuming nitric acid for this. The chip is immersed in heated red fuming nitric acid. This reacts with the plastic packaging and removes it. The chip is then rinsed in acetone and cleaned with isopropyl alcohol in an ultrasonic bath, and then you have a nice, clean, bare dye. The nitric acid is aggressive, and it's important to handle it carefully, but the process really is very straightforward. Most people wouldn't want to do this inside their home, so use the fume hood you have set up in your garage. After decapsulation, the bare chips are left with bonding wires still attached to them, so those wires are going to be plucked off just to get them out of the way. Already, we can vaguely see some of the large structures on the chip. Half of it is covered with a metal plane, and the other half does show some visible circuitry. This is an image of the chip under a microscope. It was stitched together from several smaller images so that we have an overview. Looking at the decapsulated chip under a microscope, we can see the bond pads around the outside, the metal plane that covers the top part of the chip, and wires on the bottom part of the chip. This is a spaghetti logic with lines running all over the place. And there's a couple of structures in the corner that look like a memory. So to see more of the chip, it'll be necessary to delayer it. To delayer the chip, I use hydrofluoric acid to perform a wet etch. I use the Wink rust stain remover product. It's available in hardware stores all over the USA. It's a dilute HF solution that works really well for delayering ICs. Put a small amount of Wink liquid in a beaker, heat it on a hot plate, drop the decapsulated dye in. Using a pipette, I agitate the liquid to disturb the bubbles that form on the surface of the chip, and then the acid etches the chip more evenly. You probably don't want to breathe in these fumes, so do this in your garage also, in your fume hood. The etching result isn't perfect. Some parts of the chip are going to get etched deeper than other parts, but I have gotten useful results using this technique. So after a short time in the heated Wink solution, the chip was rinsed and then put back under the microscope. The top metal plane has been removed. Now we can see what's below. There are some visual effects that we can see on it from the etching being a little bit uneven, but overall it turned out pretty well. At the top left, the tall rectangles are RAM, and the 4 blocks at the top right are ROM. And then there's some logic tying these in to the big logic area below. I was interested in finding where the bits are encoded in ROM, so I continued delayering the chip. Another dip in the Wink, another metal layer has been removed. I didn't see bits in ROM yet, so I was going to continue the delayering. Now at this point, we see even more visual effects from the uneven etching, but it's still usable. After a third dip in the Wink, more metal's been removed. At this point, the delayering is becoming more and more uneven. We can see the ROM blocks have been half etched to a lower layer, with half of the upper layer remaining. The wet etching process is difficult to perform in a very consistent manner without additional steps, such as polishing. I didn't have that available at the time. Some areas of ROM are now showing visible bits, though, but the other areas haven't been etched deeply enough. So I continue to etch further to try and get a clean ROM. So now we can see the ROM bits. They're quite clearly visible now. They're arranged in rows and columns, and in this image, if a black dot is visible, that indicates that the bit is a 1. Now, image quality is important. The better the photographs, the more consistently the bits will be visible. But it doesn't have to be really perfect. You can do some image processing. You can delayer multiple chips so that you can combine the clean areas from them. For myself, with this example, I was able to do it with only one. It turned out pretty well. With the visible bits exposed and photographs taken, the bits can be extracted using a software image analysis tool, or you can even do it manually. This ROM is 32 kilobytes, so that's over 260,000 bits. So a manual extraction is a bit labor intensive, but not impossible. The software tool is a little bit more efficient. I wrote some software to analyze the images and identify the 1 and 0 bits. Here they're marked with a yellow box for 0 bits and a blue box for 1 bits. So I use the software to analyze the image, and then I can quickly check it over and see if it made any obvious errors. After extracting the bits from the photograph, now I have a binary version of the ROM data. This is a visual representation of the bits that were extracted from ROM. The black boxes are 1 bits, the white boxes are 0 bits. In this image, I overlaid the extracted bottom 13 rows of bits over the photograph. You can see some visual patterns within the bits, and this is a really good indication that the ROM is probably not encrypted or heavily scrambled. This image shows at the end of the ROM area, and we have a really large pattern visible here. This is because there's filler bytes that occupy the unused space at the end of the ROM. Then at the very end of ROM, this pattern is interrupted. This is because this is where the vectors table exists at the top end of memory. This is where they have the reset address and the addresses of the interrupt handlers and this kind of thing. So the ROM has empty space, all of these filler bytes, at the end, and then the vector table lives at addresses FF, F6 through FF, FF, right at the very end. So after extracting the bits and decoding them into bytes, the hex dump can be studied. There is a copyright 1997 CHCC ASCII string in ROM, so this is very helpful to identify when you've actually decoded the ROM correctly. The decoding is just a matter of organizing the bits into bytes, and it's in a really straightforward manner. There's no scrambling or anything like that. So now with the ROM contents extracted, the software can be disassembled and analyzed. The first step was to identify the CPU architecture. Studying the binary dump, it appeared to be an 8-bit CPU, but was not 8051 or 6805 or the other processor types I tried first. Eventually, I tried disassembling a 6502 and the code made sense. Later, I remembered looking at an older access controller from the same manufacturer, which was used in a previous system, VideoCipher 2+. It's an ancestor of DigiCipher. On this older chip, there was actually a copyright notice from WDC, who licenses the 6502 core IP, visible directly on the chip die under microscope. So this would have been a good clue to the CPU architecture if I'd actually noticed it earlier. For the disassembly, I used IDA. It includes support for 6502. It's very powerful. In addition to disassembly, I used some 6502 simulations software to study it in a virtual CPU. The simulation is really helpful when disassembling the software. It provides a lot of insight into what's going on in the software. Since 6502 is a well-known architecture, it was not difficult to find an existing simulator, even free with source code. The 6502 was used in 8-bit computers like the Apple II, Commodore 64, so there's a lot of enthusiasts and a great deal of information about this architecture. As I gained understanding of the system on chip through disassembling the software, I added some features to the simulator so that I could emulate some of the peripherals that exist inside the ACP. One of the first things I saw in the disassembly was that there were 2 operating modes. During startup, values in RAM are checked, and if the ACP has not been initialized, then it enters a personalization mode. This is used during manufacturing to assign the unit address and the seed keys. In normal conditions, after the set-top box has left the factory, this personalization software is bypassed, and the ACP always runs its main application. The next thing I found was that the application was not a really simple program. This 6502 runs a task-switching operating system. 8 tasks are run. which supports decryption of up to 2 channels at the same time from the one chip. So there are 2 tasks that are dedicated to processing the ECM40 messages, and those generate working keys that are used for the transport stream decryption. There's 2 tasks that handle processing of the ECM41 messages. Those generate program keys that are used to process the ECM40. One task handles the EMM processing. There's also a task to handle the TV pass interface, and there's a task to handle messages that come in from the SPI interface. Since the ACP is a custom system on chip, there's no documentation available describing the hardware capabilities. So the disassembly was studied, and I/O registered had to be guessed based on their usage in software. There's an SPI slave peripheral for communication with the set-top box main controller. The SPI peripheral sends and receives data directly to RAM, and a signal is set to indicate when the transfer is complete. There's a DES crypto peripheral. The key, data, and operating mode are set in registers, and when complete, the result can be read from additional registers. There's a transport stream descrambler. The working key is set in a hardware register, and then the descrambler will seamlessly output the decrypted transport stream on the serial transport stream interface. There are also PID filters. These are set by the main controller in the set-top box over the SPI bus. So these filters select which of the video and audio streams will be descrambled, and it selects which PID has the ECM packets that the ACP should receive and process. The received ECMs are placed in RAM, and then the 6502 is notified that this exists by a register bit. So at this point, I'm starting to get an idea of how the system works. I've studied the MPEG transport stream and logged ECM and EMM data. I've logged the SPI bus, and I understand the messages between the main controller and the ACP. I was able to extract the entire ROM contents optically. I've disassembled the software, and I've run it in simulation. There are some keys found in ROM, fixed keys, which never change. These are used when a channel goes into a free preview weekend or something of the sort. Any set-top box that has ever had any kind of authorization in the past is able to decrypt these channels that are encrypted using the fixed key mode. So now the focus is on understanding the ECM and EMM algorithms that are found in the ROM software. At this point, I'm still missing some important information from the ACP. All the seed keys, category keys, program keys exist only in RAM, so to decrypt any channels not on free preview isn't yet possible. The ECM40 message is used to generate the working key, used to descramble the MPEG streams. There's a service ID used to identify each channel, a frame count that is used with the program key to calculate the working key. The frame count increments with every ECM packet. There's a crypt mode byte that identifies if the channel is operating unencrypted or with a fixed key or with the normal secure keys that are used. And there's a byte I've labeled hardware that has 1 bit set in it. This selects a special decryption mode that I'm going to come back to a little bit later. The ECM41 contains the encrypted program key that's needed to correctly process the ECM40. There's a provider ID that indicates which TV operator subscribers should process the ECM41, and there's the same service ID that matches the ECM40 message. The category epoch identifies which category key is in use. There's also information about how long this program key will be valid for. The ECM41 contains 1 or more subscription tiers that must be found within the customer's ACP to allow this message to be processed. The subscription tiers are written to the ACP when the EMM containing authorization details is received. And again, there's a hardware crypto select byte that it's going to be a topic that I come back to. So this slide shows what a half second of ECM40 and ECM41 activity might look like. To be able to descramble the program, the ACP must process a current ECM41 to get the program key, and then process an ECM40 to get the working key. The working key is then used by the descrambler to descramble the MPEG stream. The working keys have a short lifetime, only 133 milliseconds, so this series of ECMs shown here is within a period of a half a second. EMMs are split into 4 parts. Each part contains a portion of the subscription information for the set-top box. A category, excuse me, a category key is calculated from each of the 4 parts, and that key is calculated for each part must match, or these EMMs will be rejected and all the authorization data and category key will be wiped out. So this is an example of an EMM. Each of the 4 EMM parts contain some common information, like the unit address and which category epoch the EMM contains information for. The EMM can contain 2 category keys. There's one for the current epoch, one for the next epoch, so that when the epoch changes, the ACP has the new key available already. To decrypt the category key from the EMM, the seed keys contained in the ACP are used. The seed keys are unique to each ACP and are assigned during manufacturing. EMMs are transmitted out of band for cable systems, but they're passed to the ACP in exactly the same way as for satellite systems. So at this point, it should be possible to decrypt the channels that are using a fixed key mode. The analysis of ROM has shown the algorithms used to process ECMs and generate a working key. The fixed keys are known because they're in ROM. There could be some question about the possibility of bit errors from the optical ROM extraction process, but the fixed keys can be confirmed as correct because the ROM software performs a checksum of the 256-byte area containing keys. Successfully running the checksum on the extracted ROM indicates the extracted keys should be correct. But when I attempted to decrypt a fixed key channel, there was a problem. It didn't work. So whether it was a bug in my implementation or whether something else was going on was unclear, but I had noticed that a bit in the ECM40 was set that causes a bit in the ACP hardware peripherals to be set. The purpose of the bit was unclear, but its address was suspiciously close to the descrambler key, so I start to suspect there may be some encryption other than the standard DES at play. So I started to work on a glitcher to study the chip a little bit more in depth. The timing tests I did on the ACP suggested that the 6502 was running from an internal clock source, so this rules out a clock glitch attack. Voltage glitching makes sense, and with the age of this chip, it seemed pretty reasonable to expect it could be susceptible to voltage glitching. The stronger protections are generally more recent. So my glitcher design is pretty simple. It's based on the XMega board and a breadboard. I use the XMega to communicate with the ACP via SPI and to control the glitch. A 74 series 4053 analog switch is used to quickly switch the ACP VCC supply between 2 voltages, the normal level and the glitch level. I use a benchtop DC power supply with 2 outputs, so I can easily adjust both the normal level and the glitch level. The other parts on the breadboard are an oscillator to provide some of the clock inputs that are necessary for the ACP to run. There's an inverter and NAND gate that I use to cut the clock out during the glitch time. To simplify the test setup as much as possible, I removed the ACP from the set-top box and I soldered it to a breakout board. In this process, the battery-backed RAM is disconnected, so all the keys are lost, but for the purpose of developing a glitch, this was okay. So this simple breadboard-based glitcher was very flexible. The breadboard can be modified to test different ideas and can be reconfigured quickly, and I didn't really need to make anything more advanced than this. So to test if the glitcher will work, and to find what voltage levels to set it to, we can send a command to the ACP, then glitch, and see if the response is unusual. The general strategy here is to lower the voltage just to the point where the chip sometimes resets due to the glitch. By adjusting voltage levels and glitch length and timing when the glitch will land, I succeeded to cause ACP responses to be altered. The checksum on SPI packets is really convenient. When unusual data was received from the ACP with a valid checksum, this is a really good sign that the glitch caused a temporary fault and then the CPU resumed normal operation. Depending when the glitch is delivered, different effects are seen. We can see that generally as the glitch is moved later, it's the later bytes of the response packet that are getting changed. So at this point, it looks like the glitcher works and is able to cause a brief fault in this chip. Since I had an effective glitch, I took the circuit from the breadboard and etched a simple PCB that could plug directly onto the XMega development board. This performs exactly the same function as the breadboard did, but I'm a lot less likely to accidentally unplug a wire from the breadboard and have to repair it. The circuit was simple enough to create a one-sided PCB, so I just etched it at home. Now my goal is to have the ACP execute the code of my choice. Because the 6502 is a von Neumann architecture, all the code and data memories share the same address space. From the software disassembly, I've seen that there doesn't appear to be any kind of paging or MMU features. The software in the ROM is fully self-contained. There is no EEPROM, and the RAM is never used to hold executable code. So there's no jumps into these areas to exploit, and it wasn't really clear at this time if there was anything actually preventing code execution outside of the ROM. So I decided to take a chance and test if the RAM was executable. I send a message via SPI. I know that this is going to be stored in RAM. This message contains 6502 executable code that will copy itself to an unused area of RAM, execute from this area, send an ACK indicating it was successful. Because I've already studied the use of the SPI interface, I was able to create this executable payload that will continue to receive commands via SPI after it's taken control of the ACP. So my strategy is to send code to the chip, where it goes into RAM, then glitch to cause an instruction to be misinterpreted, hoping to cause a jump into the area in RAM where my payload sits. To try to maximize the chances of success, I looked through the ROM code for multi-byte instructions, which, if broken up, contain within them a jump opcode with a destination that should lead to where my executable payload is placed. Since the ACP has a single address space, this gives really a lot of opportunities for glitching to cause execution to reach the code payload. There's multiple scenarios possible in addition to the one that I selected to target. Stack corruption is a possibility, and really any abnormal program flow has some possibility that it might eventually land in my code. So a von Neumann architecture without strong memory management is really fertile ground for glitching. Anything in RAM potentially could be executed. At this point, there's several uncertainties, but so far I wasn't able to rule out this being possible. The ACP does run from an internal clock source, and the interrupt-driven task switching adds a little bit of further timing uncertainty. So I will send the code payload, delay, then glitch, and see the result. When it's unsuccessful, I change the delay and try again. I try to aim for the instruction I've identified as possibly corruptible to a jump, but there's so many unknowns that the process is like fishing. Throw a line out and hope. And sometimes fishing is good. Relatively quickly, the ACP returned an ACK that told me it had a successful glitch. This first successful glitch took some hours to find. After that, it was possible to make it work repeatedly within a matter of minutes or often even seconds. So now I have executable code sitting in RAM. I'm able to send the ACP additional pieces of code to be executed. So at this point, I can read any memory address, I can write any address, or perform any of the other operations that are possible with this 6502. So I wrote a simple application that performs the glitch searches and then can interact with my code payload backdoor I've installed in RAM. This program allows me to enter an address and length and have data returned or to write to memory, etc. There's also support for setting the key and data and performing des, encrypt, or decrypt using the hardware peripheral inside. At this point, I noticed a few points about this chip. There's a 2 kilobyte area of ROM that, if I attempted to read, causes the chip to reset. This area of ROM contains the personalization routines, and those are never supposed to be used after the device leaves the factory. There's also protection against modifying the seed keys in RAM. Trying to store a value to these locations appeared to do nothing. There are specific addresses within RAM that can't be read, or the chip will lock up. These are clever traps put in as a safety measure. The 7-byte, 56-bit keys stored in RAM straddle these dead addresses. So any potential exploit that could cause a linear dump of memory will be stopped before you can even read a complete key. When the chip is reset, this means that I have to glitch in again because my code payload exists only in RAM and there really is no way to hook in any kind of permanent backdoor. Since we can execute code on the ACP and receive a response, we can read the ROM and have its contents without any of the errors from the optical extraction process. So I compared the results from the optical ROM extraction with a proper dump I got. I can see how many errors were in the optical extraction. They're marked in red. Overall, the extraction was pretty good. It was good enough for me to get to this point. There also was only actually 1 byte within the dump that had more than 1 bit incorrectly flipped. And many of these errors are actually obvious when disassembling the software, because if an instruction looks really out of place, but changing a single bit makes it sensible, probably it's a bit error. So I didn't actually keep detailed records about this, but I think I probably caught about half of the bit errors during the disassembly process. So the interesting keys in the ACP are all stored in the RAM only. This includes the working, the program, the category, and the seed keys. The RAM is battery backed. If the seed keys are ever lost from RAM, the ACP can no longer process ECMs. It can no longer process EMMs, and so it's totally useless. It's possible to glitch the ACP and read out memory, but my glitcher works with an ACP that's been removed from the set-top box. When the ACP is in circuit, the connections to the other components and it having 16 VCC connected pins pose a bit of a problem. So to glitch the ACP in circuit is going to require some modifications to the set-top box, disconnecting it from the other parts. Or another alternative was to remove the ACP from the set-top box and place it on a breakout board without losing battery power and wiping RAM. So rather than modify the set-top box, where each of the several different models were going to require unique modifications, I decided to try removing the ACP with the battery still attached. The plan is to carefully lift the ACP battery and ground pins while the set-top box is powered on, so that provides VCC. So I use a small tool I made from a razor blade. I cut it out using a Dremel tool. I attach it to the handle with a screwdriver. This tool could be wedged under a pin, and then some hot air on the solder will release the pin, and the pin can be lifted straight up without damaging any of the other pins. So at this point, I have an ACP inside of a set-top box that I have an external battery connected to. It's still inside of the box and still working. So at this point, I can load up the pins with a lot of flux, put some hot air on it, and very carefully lift up the chip without letting the solder on the battery connections melt. So now I have it hooked up to my glitcher, which is now inside of a box. It looks much nicer. And I can now start to glitch the chip with the battery on it, so the RAM is valid. When I started to glitch, I found that my timing had changed, so I wasn't really sure if this was due to some different oscillator settings or if there's a different code path because the other chips had wiped RAM. But anyways, by modifying the time of my glitch, I was able to get the same glitch to work, and then I was able to execute my code on the chip with the valid RAM. So for the transport stream scrambling, since I can now run my own code on the ACP, it was time to really study this in depth. So there's a hardware register bit that is set or cleared based on one of the bytes in the ECM40. When this bit is clear, standard DES is used. When it's set, the descrambler acts differently. There's also an 8-bit hardware register in the DES peripheral area. When it's 0, it's standard DES. For any other value, it acts differently. So at this point, I started to wonder if I might be looking at actually having to do a gate-level reverse engineering of the chip to understand this functionality. It's using technology that's older, so it should really be feasible to do it. But if possible, I'd like to avoid it. It'll be a lot of extra work, time-consuming, and it might tend to give imperfect results like the optical ROM extraction. So I start with trying to characterize the scrambling modes. The transport stream packet is made up of a 4-byte header and 23 blocks of 8 bytes each. DES operates on these 8-byte or 64-bit blocks. By flipping one bit in the encrypted input, ECB, CBC, or OFB modes can be differentiated. Flipping one bit causes an 8-byte block to be corrupted and the corresponding bit in the following block to be flipped. This indicates CBC mode is in use. Timing the transport stream input compared to the decrypted output was measured with the descrambler in the standard mode and the custom hardware mode. No timing difference was seen. This suggests that the internal properties of the DES haven't really changed. Same number of rounds, all of this. And this makes sense because the decryption has to be done in real time, so they can't really change the timing. Also, by using an ACP as a decryption oracle, I determined that this customization was affecting each of these 23 blocks of the packet a bit differently. So next, I tested the hardware using DES weak keys. These are certain keys that are not recommended to use with DES because their properties weaken the cryptographic strength. A key of all 0 or all 1 will cause the DES encryption and decryption to be identical. That means that running the same data through encrypt or decrypt will give you the same result. I can test this on an ACP configured for standard DES decryption and see the expected weak key behavior. When I tested it with the descrambler in the custom mode, the weak key behavior changed. Using a key of all 0 or all 1 doesn't produce the same results in encrypt and decrypt modes. I also tested the DES peripheral with different values in the 8-bit register and using the weak keys, and it showed that the DES weak key behavior did still exist. So at this point, my hunch is that one customization affects the key and the other customization affects the data. At this point, I can't be certain, but I have a good feeling about the theory, so I continue to investigate it. Based on the idea that the hardware customization is only affecting the key and the decryption timing is static, I thought the simplest customization would be an XOR mask that gets applied to the key before it goes through the DES decryption. XOR requires only a single gate in series with the DES engine, so it fits all the requirements of fast and simple to implement in hardware. A change of even one single bit in the key would cause the effects I observed. Flipping more than 28 bits of the key is pointless because that's really the same as inverting the key and then flipping fewer bits. More flipped bits would also mean that they have to add more gates into their customization, so it seemed reasonable to expect that they might flip a minimal number of bits within the key. So I wrote this very nice for loop that's nested 16 levels deep to test the decryption results after flipping 1 bit of the key, then flipping 2 bits, then 3 bits, and so on up to 16 bits. To test all the possible keys this way is going to take a long time, but if only a few of the bits were flipped, then it might be identifiable in a shorter period of time. And promising results did come quickly. It turns out that the theory holds up, and some of the blocks have as few as 3 bits flipped in them. This took only seconds for the software to identify. After verifying that these XOR masks did work on these blocks, I left the software running and it was able to find all of the 23 XOR masks. This very simple brute force method worked. I ran it for a couple of days to get all of the 23 blocks. By analyzing which of the bits are being flipped in the early results I received, a pattern can be found so that you can limit the search a bit more. Using this technique, a software cracker can complete the process of identifying all of the 23 XOR masks in 1 second. So after successfully solving the first hardware customization, the theory that the second customization is a data XOR really looked promising. So it made sense to me that one or more XOR gates on the data would be enabled by each bit of the 8-bit hardware register. So using the ACP as a decryption oracle, a known key and data were decrypted with all values of the 8-bit register. Software attack of this function was successful, and 255 XOR masks were identified with behavior matching exactly what I expected. Now, I haven't actually seen this hardware customization in use. I presume the functionality was saved so that it could be used as a countermeasure against pirate devices if necessary, but it was never necessary since the system was never breached. In order to implement a softcam, this is a software implementation of the descrambler, a few more cryptographic details need to be identified, but at this point, I have all the tools to do so. The initialization vector used for CBC mode can be found through a simple XOR, and the handling of short blocks, those less than the 64-bit DES block size, can be identified likewise. Now, with all these details, a software implementation of the EMM decryption of category key and ECM decryption of program key and working keys can be made. And the transport stream descrambler can also be implemented in software. The rapid key changes in the use of DES with the hardware customizations make it a bit different to implement compared to a softcam for a typical DVB system, but overall the concept was the same. And now it works. I was able to test it. It was fully working on both the satellite and the cable systems. This is the screen that's broadcast before a pay-per-view event goes live. The pay-per-view, like all the other channels, can be decrypted by the softcam using the algorithms learned and these keys extracted. So I identified some weaknesses within the system when I was studying it. The first was that it's now pretty old technology. This makes it a lot easier for an invasive analysis today. The TQFP 100 package was actually pretty easy to deal with compared to what some of the modern alternatives are. The chip is susceptible to voltage glitching. The von Neumann architecture with no strong MMU protection meant that I could easily put my code in RAM and then have it executed. They don't include any possibility for any kind of a code updates, so they have no software update mechanism for any countermeasure purpose. And really, their hardware crypto customizations were pretty simple. I was able to guess them. The strengths, I was pretty impressed with the system overall, actually. The key handling and the decryption contained within one single chip makes it really difficult to do any kind of a key sharing. The fast key change interval would also make key sharing very difficult. The fact that there's no possibility for code update means that there's nowhere that you can write a permanent backdoor. So overall, I think that this feature is actually more of a strength than a weakness, because at the point when you need to do a code update in the field, your chip's already hacked, the hackers already have the ability to read your update anyways. The internal clock for the 6502 meant that I couldn't clock glitch, and it made it a little bit harder to time the glitch position. Their dead addresses that they put in the middle of the key space is very nice. This prevents a linear readout of keys and would really stop a whole class of attacks against it. The personalization area in ROM that they use to write the unit address and the seed keys initially seems to be accessible once they complete that mode. All of the keys exist only inside of RAM, so you have to have the battery all the time. So this rules out a lot of different invasive attacks to try and read the key out. Also, the keys, I wasn't able to rewrite them in RAM. When I would try to store a value there, nothing would change. So this is a nice protection against just cloning a box to be an exact copy of another subscribed unit. All of the EMMs are addressed to individual boxes. They don't send anything down to a group. So this means that if you want to get active keys, you have to actually pull keys from a box with an active subscription so that they send a key that is addressed to you. Generally, the software appeared pretty well designed and written. I didn't notice any glaring software bugs inside of it. And although they're using 56-bit DES, they use 3 DES keys in combination when they're processing the EMMs. And in all of the ECMs, they're using multiple rounds of DES. It would really increase brute force complexity. I didn't see any obvious weaknesses in that area. So a note about TV piracy. I don't advise pirating satellite or cable TV. There's really nothing good on. I looked. It's not worthwhile. Thank you. I really appreciate the chance to talk here. This is really exciting for me. I had a lot of fun with this project. I learned a lot. If there's any questions or anything, I would be happy to take them. But this is about all I have. Yes? For the main transport stream or for the out-of-band transport stream? Okay, for the out-of-band transport stream, I wrote some software that did the de-randomization of these things on the raw transport stream because I was getting it directly out of the QPSK demodulator. For the main transport stream, all the demodulation is done and complete before it goes into the ACP. So it looks like a normal transport stream, just encrypted. So after the software decryption, then I could feed it right into VLC.
Can you just repeat the question?
sorry. Yeah, the question was if there was any processing on the transport stream that I had to do after decryption. Yes?
Thank you. About the dead addresses, would that actually cause chip lockup or wiping of the keys, or what was the impact? Did you lose a few chips of the ACP and had to get new ones?
No, as far as I could tell, all it does is cause a chip reset. The dead addresses actually didn't cause me any problem because when I was studying the software, I could see that they would read specifically from address 0, 1, 2, skip a byte, 4, 5, 6, 7. So this looked very unusual and tipped me off that there was something going on there. And then at the point when I actually had access to talk inside of the chip, then I could poke around a little bit. But no, when those dead spots are hit, there's no bad reaction. It just resets the chip, so I didn't lose any to that. All right, well, thank you very much for listening. I really appreciate the chance to talk here. This has been great.